Okay, physics. So let's look at projectiles that are launched at an angle. So first, a couple of general things to think about. So I'm going to have a projectile. It's going to be thrown at an angle. Of course, this is an armadillo, so there it is. Count the number of stripes. Make sure he's got legs. So he's going to be thrown off at an angle. Once he's let go of, that he's going to follow this parabolic path. So this should not be a surprise to you, right? So you've seen this before, or you've seen an object that's been thrown before. So it's going to follow this path. And at any point along this path, right, we can think about the horizontal and vertical velocity. So here I have horizontal velocity going in this direction, and I also have vertical velocity, which is going upwards. As I get towards the top, I still have the same horizontal velocity. Remember, horizontal velocity is not going to be affected by gravity. My vertical velocity is so it's being accelerated in the opposite direction, so my vertical velocity is becoming less. And when we get to the very peak, oops, that should be the same length arrow, but my vertical velocity becomes 0. And as I get over here, I start now gaining vertical velocity, and my horizontal velocity remains the same. So, and a few important things to recognize. So there is a point where my vertical velocity is 0, and that's going to be at the top. And this is a handy thing for us to try to do because it separates this into half. So how long does it take to get there? Well, let me think about this, right? So if the total distance from beginning to end is d, then the distance to get to the top is going to be half of that. And since I'm moving at constant velocity, the time it takes to get there, if it takes me time t to go all the way, then it will take me half as much time to get this way. So it's a handy thing to know that when I get to the middle, my highest point, that's when my time is half as long as it's going to take to get back to this position, and I've traveled half my total distance. One way to think about this, and when I get to this point, is essentially like a cliff problem, right? So here's a cliff problem where I'm throwing something off a cliff that only has horizontal velocity, and it gains vertical velocity as it goes along. And if I wanted to, I could just double that, right? So how long does it take? If I know how high something goes, I can figure out how long it's in the air, right? So I'm going to say, well, if I do this half of it, and if I just drop something from this height, the time it takes to hit the ground will tell me how long it takes for this leg to happen, and I can double that to find the total time. So anyway, a few ways to think about these things. So sometimes it's helpful to think about just the leg up, so going from maximum vertical velocity to 0 vertical velocity. Sometimes it's helpful to think about things just on the way down, and sometimes we're looking about all the way across. But again, key for this, just like the cliff problems, is to separate the horizontal and the vertical dimensions, and then find the connector. A lot of times the connector is time between those two, and make sense out of it. So let me do I'm trying to do 2 problems for you. One, a straightforward one, and then I'm going to throw a little bit of curveball in there. And you see that if you're really careful and consistent with the math, it's just the same equations that we use them and lay them out carefully. So let's throw our armadillo up. So let's say he has has an initial velocity of 25 meters per second. Whew, he's going, and I'm going to throw him up at some angle to the ground. I don't know, say 20 degrees. He's going to travel, and I want to know how far is he going to go. I want to know how far he's going to go. Well, again, I'm going to separate this into 2 dimensions. Right? So I'm going to have my vertical dimension, and I'm going to have my horizontal dimensions. So my vertical dimension, I'm going to use y to represent my vertical dimension. So my starting position is going to be at 0, and when it comes back down, my ending position is also going to be at 0. What else do I know about this? So it has initial velocity in the y direction. Well, I got to think about this, right? So I've got a vector. As I promised, I'm going to have to separate all these vectors. Whenever I see something at an angle at this point, this is 25 meters per second. This one opposite is sine, so this is going to be my hypotenuse times the sine of that angle, and this is going to be the hypotenuse times the cosine of my angle. So my initial velocity in the y direction is going to be this 25 sine of 20, My final velocity, let me think about this. So I throw something up, we're ignoring air resistance. If I throw something straight up, when it gets back down to that same point, it's going to have the same magnitude of velocity, but in the opposite direction. So technically, I know the value for the final velocity in the y direction is going to be minus 25 sine of 20. Pretty handy when it lands at the same level. My acceleration is going to be negative g, and the time it takes, well, I don't know, sometime t. In my horizontal direction, I know my what do I know? I know my starting position is 0. My ending position, I want to find, I'll call that d. My initial velocity is going to be 25 cosine 20, and that's also my final velocity, so there's no acceleration in this one, so the velocity doesn't change, and the time it takes to do that is t. Let me think about this, right? So I want to get to d, but I don't know t, so if I know what time is, then I can figure out what d is. So time is my connector here, so I'm going to figure out time from this information. What should I use? Well, heck, I could use any equation really. So let's use this one. So y is going to be y naught plus v naught t plus 1/2 a t squared. Why not? So what do I know about this? So I'm going to cross out my zeros. Again, I'm not going to solve this for numbers to get to time unless I'm asked to, but I'm going to solve it algebraically and then plug it into to get to another equation. So in the end, I'll only use my calculator once. Okay, so let's see. So I'm going to cross out the things that are zeros. So this is 0, that's 0. So I'm going to have v naught in the y direction. Be careful about this. V naught in the y direction times time. I'm going to divide everything by time. So if I divide 0 by time, that's still 0. Divide this by time and divide this by time, I'll get rid of the square. So I'm going to end up with 0 is equal to 0 plus my initial velocity in the y direction plus 1/2 a t naught squared. I'm going to plug in negative g here. So I'm going to, and then move this to the other side. So I'm going to have 1/2 g times t is going to be equal to v naught in the y direction. And I'm going to solve for time. So time is going to be 2 v naught in the y direction divided by g. Not so ugly. Now I want to go to my, oh, there it is. So, and that's what I ended up with. Check and make sure it makes sense to you. So now I'm going to go to my other dimension. So here it's a little bit easier, right? So I'm going to use the velocity is equal to acceleration times time, change in displacement over time. My change in displacement is going to be d, so velocity is equal to d divided by time. I know velocity, this is my x direction velocity, so I know velocity in my x direction. So I'm going to say my distance is going to be equal to velocity in the x direction times time. So now I'm going to plug this in for time and combine these together and try to make sense of it. So d is going to be velocity in the x direction times this to velocity in the y direction that I start with divided by g. And now I can get to the point where I just plug in numbers. So I know velocity in my x direction is going to be 25 cosine 20. Velocity in my y direction is going to be 25 sine 20. And g is going to be 9.8. And I'll trust you can plug it into a calculator and get an answer from there. So that's the idea, right? So I'm using the same kinematics equations that we've been using. And I'm just being really careful about how I lay it out so it makes sense. I'm going to stop here and do a harder one on the next video. Thanks so much. Bye.